Combustion can be a very tricky process, but it's absolutely necessary for any chemical rocket to work. We created a lesson on rocket engine ignition, and we've covered the basics of thermodynamics in some lessons. This lesson is going to teach you the ignition limits of different fuels, the energy produced by combustion, and the thermal limits of our current rocket engine materials. We covered explosions in this lesson, but it seems someone wasn't paying close attention. So we'll reinforce a few points. Get ready for the science of combustion. How to make your rocket fly without blowing it up. Rocket fuels come in several different types. We're going to look at hydrogen, methane, RP1, hypergolics, and solid propellants. For oxidizers, we will consider liquid oxygen, nitrous oxide, hydrogen peroxide, dinitrogen tetroxide, and perchlorates. Combustion, as we use the term here, is the process of oxidizing a substance, thereby creating a chemical change that produces heat and light. Let's look first at solid rocket motors. These motors have fuel, usually a hydrocarbon like hydroxyl-terminated polybutadiene, with a metal fuel mixed in like aluminum, titanium, or magnesium. Again, this is one of the fuels. Others can be used like nitrocellulose, which is basically paper and nitroglycerin, or plastics. Mixed in with these materials is an oxidizer, quite often a perchlorate, like ammonium perchlorate. We can see that the fuel is both hydrocarbons, which burn to carbon dioxide and water, and the metals, which burn to metal oxide. But these materials don't spontaneously ignite. They need an igniter. Here is the M57 rocket motor igniter assembly. This is like a large model rocket motor, which, if you are building and testing a new rocket engine, is one of the simplest ways to reach ignition. Simply install a small rocket motor with its electric heating element in place, and when electricity goes through the heating element, it will glow white hot. This will reach ignition temperature for the little motor, which will burn for several seconds. The heat generated by the little motor can ignite the large solid rocket motor. Once ignited, the solid materials start to burn. These little motors are called pyrotechnics, by the way. The heat provided by these pyrotechnics causes the chemicals combined in the motor to break apart. Once apart, they spontaneously reform at a lower energy level, giving off the excess energy as an exothermic reaction. This produces a lot of heat and light. The solid materials are vaporized by this heat and light and go on to recombine again, and you get a boiling porous reaction zone, sometimes called the fizz reaction zone, which can be visually observed on the propellant surface. The hot gases exit your rocket motor and your rocket flies. India uses very large solid rocket motors for its launch systems, by the way. If you like movies about rockets and don't mind reading subtitles, unless you speak Tamil, this movie recently came out, and it was pretty fun to watch. The problem with solid rocket motors is that they are not easily throttled. We talked about the internal geometry, allowing variable thrust, but once you light one, it's pretty much gone. You could blow out the sides of the combustion chamber, or dump a bunch of liquid nitrogen down the core, but now you're adding mass and complexity. You might as well go with a hybrid rocket motor instead. Hybrid rockets use fuels like the HTPB we saw above, as well as paraffin wax and plastics, even nylon. But if these happen to be transparent, it's necessary to darken them with carbon soot or something else, so the light from combustion doesn't shine through and heat the rocket. We want all that nice heat going into combustion. Hybrid rockets are somewhat unique in that they have an ablative cooling system built into the combustion chamber. The heat of combustion is carried away in the vaporized products of combustion. A hybrid rocket does not embed the oxidizer in the fuel, like a solid rocket motor does. A hybrid rocket usually has a gaseous oxidizer. This can start with liquid oxygen, nitrous oxide, or hydrogen peroxide. These oxidizers all have different strengths and weaknesses. Nothing gives you more oxygen, however, than pure oxygen. Compressed and cooled into a liquid, it is usually at about 70 kelvins. This oxygen is sprayed down the core of the solid fuel engine. Pumps are used for big rockets, but smaller ones can be pressure fed. Hydrogen peroxide can be sent over a catalyst bed and can pressurize itself. Nitrous oxide, when it's being pumped, will actually break down into oxygen and help self-pressurize the tank. Once the oxidizer is in with the fuel, an igniter is fired. It can be another pyrotechnic or a small gas-fed blowtorch. Either way, the ignition temperature is exceeded. Now let's look at liquid bipropellant engines. These engines will aerosolize the liquid into a gas and usually mix them with a pentyl. These two gases will be very explosive in combination, like a cloud of unburned methane and atmospheric oxygen, for instance. But at anywhere near normal temperatures and pressures, these will float around, not reacting. If we put these gases in an enclosed container and heated the container, they would eventually auto-ignite. From what I can find, the auto-ignition temperature of methane when mixed with oxygen at normal temperature and pressure is about 600 Celsius or 873 Kelvin. When the gases reach this temperature, they will just explode. But even South Texas doesn't get that hot. The ambient temperature down there shouldn't exceed about 44 Celsius, which is 105 Fahrenheit or 314 Kelvin. But a spark or other heat source might exceed the ignition temperature in a very small location. Once ignition occurs, the release of energy ignites the rest of the fuel. For SpaceX, something created a local temperature high enough to ignite this cloud of methane. Figuring out exactly what this was is difficult. When glass bottles were more common in America, people would throw them away. Some of these bottles had a lens-shaped clear glass bottom. Sunlight shining through this bottle would sometimes focus just right on dry grass and start fires. The space shuttle used these spark generators to burn any hydrogen gas that slips out. The hydrogen-powered Delta IV rocket just lets the hydrogen burn in the open air. Since it's not contained, this is a conflagration. The loud boom under the Starship means ignition might have occurred in one of the engine bells, creating a contained explosion at this location which spread to the rest of the gas. Here you see some graphs showing the ignition temperature of methane related to its concentration and pressure. High pressure crams the molecules together and increases the chances they will react. It takes a lower temperature under high pressure to ignite a gas. The Raptor rocket engines operate at about 300 bar. A bar is 100,000 pascals, and this comes out to 30 million pascals or 30 megapascals. That would be about here. So ignition temperature is determined by the type of fuel, the chamber pressure, and the temperature of the gas. When hot methane and oxygen come together in a Raptor, a simple microwave emitter might be enough to get it burning. For our rocket, if we didn't want to use a pyrotechnic device, we could use a chemical that burns at a high temperature on contact with oxygen in the air. Two of these chemicals are triethyl aluminum and triethyl borane. These can be combined and are called T-Tab. These chemicals explode with a green glow and were used to start the Saturn V F1 engines. Here is the ignition sequence diagram for the F1. Here at the top, you see the common shaft dual turbopump. Here is the gas generator, which burns some RP1 fuel and oxygen to power the turbopump, sending the exhaust this way, and actually down here, to put a film of dark unburned fuel down the inside of the nozzle to help cool it. You can see that film here. The pressurized RP1 kerosene fuel is used as a hydraulic fluid to activate this valve, which is held closed by the pressurized hydraulic fluid from the ground support equipment. Once the pressure in this line exceeds the pressure here, the valve opens, and fluid flows through here and opens these valves, allowing fuel and oxygen to flow into the rocket engine, while at the same time opening this valve to release the hypergolic igniter. I've included a link to a patent for a hypergolic igniter, if you want to know more about these devices. Down here, you see that the engineers of the F1 engine didn't rely on the hypergolic igniter completely. They had additional pyrotechnic igniters, just in case. This type of redundancy is why no F1 engine ever failed. Hypergolic igniters are also used on the Merlin engine today. The green flash you see is from the T-Tab, and it allows the RP1 and oxygen to start burning. Let's evaluate several different rocket fuels. Here is a Saturn V, a space shuttle, a Falcon Heavy, and an SLS. Thanks to HazeGrayArt. The first stage of the Saturn V is burning RP1 and liquid oxygen. RP1 in oxygen produces a combustion temperature of about 3,403 at sea level, adjusted to about 3,428 in vacuum, and an exhaust velocity of 2,941 meters per second at sea level to 3,510 in vacuum. That gives us a specific impulse of 300 to 358 at best. This difference is created by the back pressure in atmosphere, which slows exhaust velocity, and how the nozzle is optimized, short for sea level or extended for vacuum. The actual specific impulse of the Saturn V first stage was 263 seconds at sea level, because the first stage was optimized for thrust. It would go higher as the rocket climbed. The Falcon Heavy is also burning RP1. It has a specific impulse of 282 seconds for the boosters, and 311 seconds for the core stage. These two are optimized for thrust, to get the rocket system out of gravity drag. This one is optimized for high-altitude flight, throttling back until these two fall away. These will burn for 154 seconds, while this one will burn for 187 seconds, 33 seconds longer. Over here is the SLS. This rocket is burning hydrogen and oxygen in the core stage from this big tank through the Space Shuttle main engines, which are RS-25s made by Rocketdyne. And the boosters are burning ammonium perchlorate composite propellant, abbreviated APCP. This is the oxidizer as we explained above. The APCP is combined with polybutadiene acrylonitrile for fuel. They produce a specific impulse of 242 seconds, burn for 127 seconds, and provide most of the thrust for the Space Shuttle and SLS. The core of the SLS provides only 25% of the liftoff thrust. The Space Shuttle main engines provided about 29%. The hydrogen-fueled engines of both systems fire for over 500 seconds. Once the empty boosters drop away, these effectively become the second stage. Again, brute force is very important for the first stage, to get you out of gravity drag, while efficiency is very important for the second stage, to get a lot of mass into orbit. The hydrogen engines are burning at a combustion temperature of 2,740 to 2,978 Celsius, depending on whether it is optimized for sea level and thrust optimized, or for vacuum operation and efficiency optimized. This gives an exhaust velocity of 3,816 at sea level and 4,462 in vacuum, giving a specific impulse of 389 to 455 seconds. Just to be thorough, the Space Shuttle used hypergolic orbital maneuvering engines. Hypergolic fuels like monomethylhydrazine, used in the Dragon Draco and Super Draco engines, as well as in the Space Shuttle OMS. These burn MMH with the oxidizer dinitrogen tetroxide to produce a combustion temperature of 4,074 to 4,091 Celsius. This creates an exhaust velocity of 3,413 to 4,071 meters per second. This is a specific impulse of 348 to 415 seconds. If we also consider a methane-fueled rocket like the Starship, we see that this fuel, when burned with pure oxygen, produces a combustion temperature of 3,918 to 3,922 Celsius, with an exhaust velocity of 3,414 to 3,756 meters per second, giving a specific impulse of 348 to 383. You may have noticed something odd. The RP1 burns hotter than the hydrogen, yet the hydrogen has a much higher exhaust velocity. When RP1 burns, the resultant products of combustion, assuming complete combustion, are carbon dioxide and water. Carbon dioxide has a molecular mass of 44 atomic mass units. The molecular mass of water is 18 atomic mass units. Temperature is directly proportional to the average kinetic energy of the molecules. Kinetic energy is calculated by the equation 1/2 mv squared, where m is the mass. This means that massive molecules going slower will have the same kinetic energy as lighter molecules going faster. For any given temperature, it is better to have low mass products of combustion. But there's something else at play also. The perfect or stoichiometric ratio of hydrogen to oxygen combustion would be 2 molecules of hydrogen, H2, to every 1 molecule of oxygen, giving us 2 molecules of H2O. This gives a mass ratio of oxygen to hydrogen of 32 to 4. This simplifies to 8 to 1. But if we reduce the amount of oxygen we use, we'll have some leftover hydrogen. Since hydrogen has the lowest possible molecular mass, we thereby increase our exhaust velocity, and specific impulse is determined by exhaust velocity. But, you might ask, couldn't we just add extra hydrogen to these other fuels? You could. If you add extra hydrogen to any of these fuels, you will get a higher specific impulse. But now you've created a tripropellant rocket engine. This dramatically increases the complexity of your rocket system, but it has been done. There are two main types of tripropellant liquid rocket engines. The first tripropellant rocket engine combines three separate propellants and burns them all together. This is called simultaneous burn. The other type burns one fuel oxidizer rich, then adds another fuel, burning them one after the other. This is called sequential burn. The Soviet RD-701 rocket engine was sequential burn. This engine burned RP-1 kerosene at launch, then would switch to liquid hydrogen in space. This engine achieved a specific impulse of 415 seconds in vacuum. This is also called mixed-mode propulsion, and was considered for the space shuttle. In the 1960s, the Rocketdyne Corporation burned a mixture of liquid lithium, gaseous hydrogen, and liquid fluorine. If we look on the periodic table, fluorine is in row 9, while oxygen is in row 8. These chemicals are, in general, more reactive than these. Lithium over here can be seen as the lightest possible metal, and the third lightest element in existence. We know that hydrogen gas is the lightest molecule possible. If the lithium and fluorine burn at a very high temperature, and the hydrogen is heated and expelled through the exhaust, this can be an incredibly efficient engine, and it was. This engine produced a specific impulse of 542 seconds. If you'll remember, the most efficient hydrogen-fueled rocket engine ever, a version of the RL-10, produced a specific impulse of only 465.5 seconds. The tripropellant combination of lithium, fluorine, and hydrogen was, however, very toxic and difficult to work with. But if we use this combination in a single stage-to-orbit rocket like the Chrysler Serve, and use fractions instead of actual mass, we see that we could get 16% of the launch mass into orbit, instead of only 12%. If we keep our dry mass at 10% launch mass, we could triple our payload to orbit by using this system. That means a single stage-to-orbit ship like the Chrysler Serve, with a launch mass of 2,700 tons, keeping the dry mass to 270 tons, could get more mass to low Earth orbit than the two-stage Starship at its current rating. Is this the limit of chemical engine development? It is not. This is a diamond anvil cell. This device is made to create pressures that would be impossible to produce with any other research device known. A similar device using tungsten carbide was invented in 1957 at the National Institute of Science and Technology in Gaithersburg by Percy Brigman. The professor was a legend in high-pressure physics and had been able to generate pressures as high as several gigapascals with his device. That's thousands of times the atmosphere of Earth. Later, his device was used with diamonds instead of tungsten carbide. These used a compressible gas, liquid, or solid, such as helium, cyclohexane, or sodium chloride, to generate and transmit pressure to a test substance. Photons like X-rays could shine through the diamond, showing the structure of the studied material. These were able to reach pressures of 1,000 gigapascals at room temperature, and up to 377 gigapascals at 6,000 Kelvin. 6,000 Kelvin is equal to the temperature on the surface of the Sun. In 2011, scientists put hydrogen gas in one of these and compressed it to 300 gigapascals, about 3 million atmospheres of pressure. This is closing in on the conditions at the heart of Jupiter. When hydrogen gas is cooled or compressed, it can become liquid at 20 Kelvin. If the pressure is high enough, it can be liquid at higher temperatures. At about 14 Kelvin, hydrogen can become a solid. But when compressed under extreme conditions, like in Jupiter's core, it is believed it can become a metal. Metals share electrons, making them very dense. In 2011, scientists thought they saw this transition, but were not able to prove it. And in 2016, scientists at Harvard University announced that they had synthesized metallic hydrogen in a diamond anvil cell at 495 gigapascals and 5.5 Kelvin. If we could produce metallic hydrogen in mass quantities, it would change everything. Metallic hydrogen would strangely be a shiny liquid, somewhat like mercury, and it would be the ultimate rocket fuel. Burning with oxygen, with a theoretical specific impulse of up to 1,700 seconds. This makes it almost twice as efficient as a nuclear thermal rocket engine. That would allow us to get to orbit with propellant tanks holding 44% of our mass. That means spaceships that look like jet airplanes would be possible. There's one more thing you can make in a diamond anvil. If you put oxygen in one and put it under about 10 gigapascals of pressure, this becomes this. This is octaoxygen. This is a very dense solid form of oxygen that is red in color. In octaoxygen, 8 oxygen atoms join together into one compact molecule. Using metallic hydrogen as a fuel and octaoxygen as a solid oxidizer, we could create a unique hybrid engine. This engine would spray metallic hydrogen down into a solid cored motor of octaoxygen with a little regular oxygen gas. We would then ignite the hydrogen, causing the metallic hydrogen to start burning with the octaoxygen. Such a dense, powerful rocket engine would finally allow us to have personal spacecraft without using nuclear power, and would probably be the ultimate chemical rocket engine. Something to think about. Thanks for listening. Please don't forget to like and subscribe. Don't forget we have items available in the Academy store, and stay safe at Astra Pro Terra.